Okay, let's get started. So let's first off talk a little bit about housekeeping. So you all have a homework due today. I'm collecting them right here. So just make sure you turn that in. I think you all probably saw that was a short one. I mean, did that homework seem to take very long? It was a tiny one. I'm sorry about the next one. No, the next one isn't too bad. I think there's only 3 problems on it, but they're not anything like the problems on homework number 3. They're longer. So on homework number 4, if I remember correctly, there's 3 problems. There's the design of a beam with an unknown cross-section, design of a beam with a known cross-section, and a slab. After today, you should be good on the first 2, I think. The slab, we will handle the slab a little later, but the design of a beam of a known cross-section and the design of a slab are kind of the same thing. So I think that will make sense as we discuss that. So other than that, any questions? One thing I'll mention, so for those of you in steel design, we have a celebration coming up next week. Concrete's the week after. So I made it a point to make sure that my steel design and concrete design exams were not on the same weeks. So I try to be nice on that. I can't help it, though, if you've got 7 other celebrations going on. It's that time of year, it's that time of the semester where us professors are going, man, let's see how many ways we can torture the students now. So I wonder if these qualify under the 8th Amendment. Okay, so what I want to do is I want to just sort of jump right back into our design example. So we made a really, really big dent into this example. We didn't quite finish it, but we got really close. So we have a 22-foot long beam, a superimposed dead load. Pop quiz, what's superimposed mean? No, it's where it's on top of the self-weight. Remember, so superimposed means you have the self-weight, and superimposed load is load on top of the self-weight. So we have the beam self-weight, and then we have a 1 kip per foot superimposed on top of that. And then 2 kips per foot live load that's already reduced, and our material properties accordingly. Let me sort of just go through this. So give me 1 sec. All right. So we have our, try and make this a little more organized. So we have our beam, and we went through the step-by-step process, and I'd say we went through, out of 9 steps, we went through, I think, 8 of them, because we have the beam designed. We have one thing left to do, and that's to analyze the beam, because we made a lot of assumptions in order to get to where that beam is now, and so we need to verify those assumptions. So let me just recap. So we had our system parameters, and then we said step 1, we're going to compute the factored moments on the beam. So we made some assumptions right off the bat to get an idea of what the beam looked like, and we got a self-weight of about 140 pounds per foot. I'll go ahead and tell you, that's not going to be anywhere near what the beam actually weighs, but at least we have something to start with. So we factored those loads to get a factored load, and then WL squared over 8 to get a factored moment. And so that step did take a little while. The other steps were a little shorter. So we took that MU and we said, okay, now we need to compute a required capacity of the beam. So in order to do that, we assume a phi value of 0.9. Again, we would love it if that actually is the case. So we'll have to verify that later. But again, we might not be. We also converted that to inch kips because of what we're going to do with it later. We got our row design value of 0.012. And then using that, we can compute a BD squared. And so we got a BD squared of about 5,700 cubic inches. And this, as you can see, we converted that to inch kips so that all the units were copacetic. Required beam dimensions, we assumed a B over D ratio of 1.5, or D over B ratio of 1.5. So using that expression, we can basically derive what BD squared would be, set that equal to this, and just solve for B. And so when it was all said and done, we solved for B, and we got something like 13.7 inches. Well, you're not going to form up a beam of 13.7, so let's just round that up. So we rounded that up to a B of 14 inches. D is 1.5 of that, so that's 21. And then H equals D plus 3, common assumption, so we got 24-inch height on the beam. Now we know the actual size of the beam. Use rho BD to get a required area of steel. And then from that, it's using the beam design aid. I think it's supplement 2, but I also gave you all hard copies last time. Using the beam design aid in order to go through all of the permutations of areas of steel that would make sense, and then checking those permutations to see whether or not we can actually fit them in a single layer on the beam. And so when that was all said and done, we came up with 3 options that would actually fit, and we went with the one that had the least area, and so that's where we left off. And so now we have a beam. We actually have a beam that we can analyze. But the big thing is, the big thing that we have to do is we have to go back and we have to validate all of those assumptions. Remember, we made some guesses. We don't know if those guesses are right. We guess the self-weight. We have to go through and probably just analyze, the capacity, determine PMN, et cetera. So, everybody good? Okay. So, one thing I think I'm going to do, I'm going to use the thicker pen. I'm going to see if that's a little clearer. I don't know. I've been writing on this. I've been looking at maybe thickening that up a bit would make it a little easier to read. You tell me. That's true. But maybe that's even better, so y'all can read it. Is that better? That better? Okay, good. All right. So, the first thing that I'm going to do is I'm going to go back to step number 1, and I'm going to analyze this beam and basically determine an MU. So the way I'm going to start that is I'm going to say, okay, what's the self-weight? So it's gamma times B times H. So now we have a new B and a new H. So we've got 150 pounds per cubic feet. And then we've got, now what was B and H? I think it was 14 and what? And then we've got to throw a unit conversion in there, just like we did last time. So these calculations should be pretty rote because we're basically doing what we did before. Let me close that. And so what does that come out to be? $350. Now what are the units? No, this is a weight, pounds per foot. So one thing to keep in mind, that's heavier than we assumed. What did we get when we made our assumptions? What did we get for a beam self-weight? What's that? It's something like 140. So what that means is we can't use that moment that we used before because that's not accurate. The beam is actually heavier. So we're going to have to update our WU and our MU so that it reflects what the beam actually looks like. So we have a W sub U, which is 1.2 times our dead weights. Okay, and so that's going to be that. And so that equals what? And so I just added 1,000 pounds per foot here because that's our superimposed dead weight. Everybody okay with that? $4,820 pounds per foot, or 4.82 kips per foot. Do I have a second on that? I'm going to make you do it. I'm going to make you do it. There we go. All right. So next comes the MU, and so that's WL squared over 8. Remember, simply supported beam, uniformly distributed load. If you aren't comfortable with using these types of formulas, just do the structural analysis. Draw the shear diagram, draw the moment diagram. So 4.82 kips per foot times, how long is this beam? 22 feet squared over 8. And so MU equals what? Did you square it? 291.6. How does that compare with last time? But how much? So keep in mind, while it drastically changed, our beam self-weight drastically changed, really the MU didn't change a lot. It changed a little. But I guess the point I'm making is those assumptions that we made, those choices that we made for the beam, the L over 16 and the B over 2, those are pretty reasonable assumptions to get you most of the way there. Okay, now that's the factored moment, but we need the factored capacity. We need the other end. We need MN. So if you have a singly reinforced concrete beam, you tell me. I'm not going to tell you. You tell me. How do we determine MN? You just had homework on it, so you should be good there. So what's the first thing that we need to determine? Well, we can find phi, but I mean, let's start a little easier than that. Finding phi is a process because how do you find phi? Somebody, tell me. Well, okay, so you need epsilon, right? And in order to get epsilon, you need C. And let's start from scratch. Like if I need to determine MN, what's the first value I should compute? There we go. I need A. I need the depth of the stress block. And so how do I do that? There we go. All right, is everybody okay with this? So, that's what I say, start from scratch, That's the first thing that we can compute right now is the depth of the stress block required to generate a section such that C equals T. So, help me out. So on the bottom, 0.85. What's the FC prime? 4 KSI. What's B? 14 inches. We're looking at the beam as it is, so we're not using that 13.65. Okay, what's AS? I'm going to make you somebody else. I want somebody to tell me what AS is. There we go. We're using the actual trial section. So 3.82 square inches. And what's the FY? 60 KSI. So plug and chug, and what do we got? Yes.
So on the homework, it was okay to just instead of having to start with going by feet and then saying I need where this is this, where this is this, having to work backwards and then plugging in that way. You could have just started with A and just instead of having to actually start with support.
How'd you wait?
Okay.
How did you do it?
I wrote out the equation that I needed to solve, so I wrote phi.
And you just started doing all this crazy algebra to get to phi?
No, I just wrote out phi and it said where this variable equals this formula, where this one equals this, and kind of put them in their separate columns, and then eventually we could have just started with.
That's fine.
A and just worked it out.
We're engineers. We're not mathematicians. Keep it simple. No, but it's not. In all seriousness, it doesn't sound like what you're doing is wrong. Anything that probably enhance your understanding, but you would have started your math here anyways, like your real computations here anyways. Yeah. So that's fine. That's good for, your first time, but after, it's all the same. So what do we get here?
4.82.
4.82 what? Inches. Okay, so we can go ahead and compute phi if you want, and we will, but why don't we go ahead and do mn? I mean, how do you compute mn? So we have everything we need. Let's just go ahead and do that now. What was D? 21. Now, what are the units? If I just calculate this right now, what are the units going to be? It's a moment. Inch kips. So why don't I go ahead and throw a unit conversion in here right now to just say 1 feet over 12 inches to turn this into foot kips now. So I don't have to write the answer twice, just do it once. I'm in kips, but I'm in inches. So I'm wanting to convert it to feet. So the reason why I want to convert it is so that ultimately my phi mn matches that. Yeah. Three. 0.1. All right, so we'll say foot kips. Okay. Now, can we compare that to that? Can we compare this to that? No. Why? We need phi, right? This is a factored moment. This is not factored. So we have to adjust it for uncertainty. So now let's talk about phi. If I want to compute phi, what's the first thing I need to compute right now? C. So let me scroll this down a bit. So C, how do I compute C? There we go. A over beta 1. So that's 4.82 inches over what? 0.85. Okay, and so that equals what? Remember, it is just coincidence that this 0.85 and this beta 1 happen to be 0.85. If we were using a different KSI concrete, we'd have like a higher KSI concrete, we'd have a different value for beta. Say it again. Okay, 5.67. Now, what do we need? We need the strain in the steel. What do I do? Somebody over here tell me what to do. Y'all been talking too much. .003, 2 zeros. There we go. D minus C over C. All right? So 0.003. So that's 21 inches minus 5.67 inches over 5.67 inches. And so that equals what? So 0.0081. Remember, it's going to be tiny. We good on that? Anybody second? All right, so we have two observations. It's greater than 0.004, right, which is our minimum ACI requirement, so that's good. So we'll just say good there. And 2, we know that epsilon sub t is greater than 0.005. And so what does that tell us? There we go. So we validate, or we assumed that phi was 0.9, and that assumption has been validated for this beam. Okay? Everybody good? All right, so we can compute phi mn, right? We can compute phi mn by saying 0.9 times 355.1 foot kips. And so that equals what? $319.6. Second on that? Okay. Now, there is only one check left that we need. Well, first off, is the beam good so far? Like, is it a safe design? How would we tell? We compare our factored moment to our factored capacity. So we would compare this to MU. So is it a safe design? Is it safe? Well, I'm not asking how efficient, just is it safe? Yeah, it's safe because this is the factored resistance. This is how much the beam can hold up. This is how much we're subjecting it to. So is it a safe design? Yeah, it's a safe design. That's pretty good. We'll look at its efficiency here in a little bit. Now, here's the pop quiz though. Is there any remaining check that we need to do on this beam? We checked the strain, we've checked its capacity, something else we haven't done. There we go, the minimum steel requirement. We didn't do that one yet. That's the last one left. So AS min is BWD Fy times the maximum of 3 square root of FC prime, or 200 PSI, right? So somebody real quick, what is 3 square root of FC prime? Just off to the side. Now how do you do that calculation? You put in PSI, there you go. You put in PSI, you get out PSI. So which one are we going to use? 200. So this is going to be 14 inches, 21 inches. We've got 200 PSI over what? There you go. Don't split 60 KSI, 60,000 PSI. And so what does that come out to be? 0.93. Do I have a second on that? Uh-oh. 9.8. I'm hearing a 9.8. 9.8. But here's the thing. What's the real thing we need to compare this to? What is AS? Like, what's the actual area of steel that we're using for this beam? 3.82. So what does that mean? We're good, right? The minute, like we have to, when this design was all said and done, we needed to provide at least 0.98 square inches of steel, and we provided that and then some. Like I said, usually 999 times out of 1,000, this check is a formality. Usually you're fine. You're providing way more steel than your minimum requirement. All right? Now, we just did a bunch of calcs, so I'd like to summarize what we've done in a fashion that makes sense. Okay? So let's draw a summary. And if you want, you can put a summary for step 9. Because we just did a lot. And so I think it's highly valuable to take a step back and go, okay, we just did a bunch of stuff. What did we do? All right? So help me out. What is MU? foot kips. What is phi mn? 319.6 foot kips. Okay. Now I'm going to look at the efficiency here in a second, but before I move on, is this a safe design? Yes, the phi mn, the capacity, is greater than the factored loads. Okay. The other two checks that are important is that we have verified that this is greater than or equal to 0.004, and we verified that this was greater than or equal to AS min. And so if you want what is the final result of step 9, it's this. Comparing these two and that these two limits are met. Now, we also said that there was an efficiency calc that we'd like to throw in. So let's do that. So the way that we compute efficiency is we take our factored load and we divide it by our factored resistance. And so that's 291.6 foot kips divided by 319.6. And for the sake of discussion, typically because I like to see these in percentages, here, I'll do that like as a unit conversion like I usually do. Let's multiply that by 100 so that we get our answer as a percentage. And so what does that come out to be? Like, let's write that as to one decimal place. 91.2%. So is this a reasonable beam? Yeah, this is a reasonable beam. So let's just sort of recap. What's the final answer? What is the final answer? That's the final answer. That beam. Like, the beam is the answer, right? What was the point of the problem? To design the beam. That's the answer. That's what we're after, right? Now think about it. Isn't this a whole lot better than the moment of inertia is 1,248 inches to the fourth? Like, it's a better, more real answer, you know? When I took this class, I always thought that, you know, what we were doing had just a lot more oomph to it. You know, it's not that the derivative of x squared is 2x. It's we're going to build that. That's the answer, okay? So usually what I like to see at the bottom of the page is something like this. Trial design is adequate. What is that? What do you mean? Elaborate. As long as, like, in short, and this is true on homeworks or exams, as long as you're 90% or better, you're good. I'm not going to make you go over that. You mean on this problem? You tell me. No, I mean the opposite. That's a good point. That would happen if this efficiency went over 100%. Sort of like Price is Right, you know, up to this number without going over. If we go over 100%, what that means is that the factored moments are larger than what the beam can withstand. So we want this number to be as close to 100% without going over. What you're saying is, what if it's lower? Now, let's be clear. Are you asking me about an exam, or are you asking me about real life? First off, let's look. I design my exams so that, you know, I use the rule of 3. And I've always done that. I don't think I've ever steered anybody wrong before. Y'all have been with me through a few rumbles. And this isn't any different, okay? So I design my exam so that if I can get it done in 20 minutes, you can get it done in an hour. So I'm not going to do that to you. And my exams are designed to reduce the iteration. That's exams, that's not homework. I can make you iterate like crazy on the homework because I can be a jerk during homework time. But let's have this discussion, okay? So I'm curious. You asked the question, I'm going to direct it at you, and we're going to have a little bit of discussion. Let's say that was 81.2%, and you had to make this beam more efficient. I'm asking you, what would you do? You brought up the question, so I'm going to pose you to give me the first response. Okay, but all right, give me one. Like what dimension? So let's make sure that we're clear on the discussion. Okay? So here's the question. Well, hold on. What if efficiency was low? We'll just say low. Okay. All right, so you say change the height, but does the height really matter? Okay, so if the efficiency is low, you say change the depth. What does that mean? You tell me. If you wanted to increase the efficiency, would you make it deeper or shallower? Well, think what's that going to do? It's going to make the beam stronger. If the efficiency is low, the beam is too strong. So what are you going to do? So you're saying, well, okay. That's a great question. The 0.98 square inches is just an absolute minimum requirement that every beam has to withstand. But that is independent of the moments that we're actually placing on it. In other words, if I lowered the load on this beam, that 0.98 would still, that limit would still be there. But we could just decrease AS a bit. That's a great question. So the question was, do we have to go back to step 1? The answer is no. We have the beam. We could just change a dimension and redo step 9. And by the way, there's this little program called Microsoft Excel that all you have to do is change a number and boom, it does everything for you. So that's sort of my point in reality. Like, don't do it by hand. Just build an Excel sheet. The calculations that we're doing, it's not like it's terribly difficult. Just change a value and, you know, I mean, how hard is it to build an Excel sheet that could calculate A or MN or C? It's not that difficult, right? So this is short stuff. So you said, so we've got lower the D, you know, decrease D, decrease the area of steel. There's more. That ain't it. So lower the load, if you have that ability, okay? So I'm going to put that as sort of a number 6. So I'll put decrease because I like decrease better. Decrease the load, but I want to talk about that one later. Did you say increase or decrease? Increase the concrete area. What's that? How? But here's what I'm getting at. You don't need to go back to row values. You've got the beam. Like I'm saying, here's the beam. What can you do to that beam to make it more efficient? You don't need to go all the way back to the row values. Like I'm talking about the dimensions of the beam. How about this? No, and I'm really surprised nobody's saying this. How about this? Well, we're going to get to that here in a second, but what about this? Nobody said decrease B. Make it thinner. That's going to change the A value and change the MN, right? right? So here, I don't like lower. I'm going to change that to decrease. Now hold on. Yes, and we're gonna talk about each of the problems with these values later. Okay, now what did you say? So what does that mean? That you're right, but what does that mean? And what would we do? You decrease it. There you go. Decrease FC prime. There's one more. There's 5 fundamental parameters that affect how strong a beam is. The depth, the width, the area of steel, the FC prime, and what? Fy. We could decrease Fy. We could decrease the yield stress. No, I'm saying you've got a beam, right? So look. Here's the beam, right? We took this beam and did step 9. What I'm saying is, do it again. Just change the width and do it again. That's what I mean by like using Excel. Does that make sense?
Yeah. Out of these 6 steps, where should we start first?
There we go. Now let's have some discussions. Okay, now let's take each of these one at a time. What's the problem with these? All right. Now, let's be clear. When I say the efficiency is too low, what I'm really saying, beam is too strong. That's what I mean when I say the efficiency is low. I'm saying the beam's too strong. In other words, we need to back it off a bit. Okay? So the question is, where should you start? Because there's a lot of stuff going on. Okay? So let's handle the first 5. Okay? Here's where I would start last. Like, I'd say there's no use in doing that. The reason why I say that there's no use in doing that is because leads to unavailable steels. In other words, grade 60 rebar is pretty much, for the most part, what's around, okay? It is by and large, the most common rebar that there is, period, okay? So in design mode, I would not worry about changing your FY because there's no use. Go to Huntington Steel, go to Lowe's, that's what they got. So there's no point. Okay. Now, of these remaining parameters, I'm curious, which do you think has the least effect on a beam's capacity? I'm just curious. Of the remaining ones. The least effect. That's a really good answer, and that's almost tied for the other one. FC prime. You ought to try this just in Excel. If you take this beam and double the FC prime, you do not get double the capacity. You just don't, okay? In fact, you get a good bit less than doubled. In fact, you double the capacity, if you double the FC prime, you only increase the capacity, I think, by something like 20%. It's really not that much. So this is not effective. Okay? Now, Another thing you said was B, okay? You can change B, but there's problems with that. There's two problems. One, not very effective. And two, it leads to area of steel issues. Why would it lead to area of steel issues? Because if you make the beam thinner, you might not be able to fit the reinforcement pattern in there, right? And on top of that, it just doesn't affect things very much. Okay? So if you want the parameters that I would play with first, this and this. Make it smaller, yes. Yes. I mean, would you want to cast a beam that's 24 inches deep 800 times in a building if you could cast a beam that was 22 inches deep? That's a lot of concrete you're saving. It's a lot of weight on the building that you're saving. So I would generally change those two parameters first. And if I had a starting place, I would probably start here, okay? The reason why is because there's only a discrete number of options for the area of steel, so you'll get a real quick idea as to whether or not you'll be able to even find a pattern of steel that will work, okay? That's where I would start. If you can't find another pattern of steel that will work, right? If you can't find one, then decrease your depth, okay? Now, I do want to talk about depth for a little bit. What if the problem is reversed? What if the beam is too weak? Would you agree that increasing the depth would make it stronger? Of course, you know. How do you get moment? How do you get moment capacity? Force times moment arm, right? So the bigger the depth, the bigger the moment arm. But what's the problem with making a beam 80 inches deep? Well, where are you going to put it? But who's going to be mad at you? The architect, right? The architect wants beams that are 2 inches deep, right? But I'm joking, but I'm being serious. There is a point where you literally can't increase the depth anymore. You just can't, right? So then what? What if you have tried every one of these 5 parameters and none of them work? Like, you can't get a beam that works. Let's talk about option 6. Decrease the load. Now, what do you mean by that? How do you do that? Boom. Exactly right. Remember, how do you determine the weight per foot on a beam, right? It's the pressure load times the tributary area, right? Now, you can't change the pressure load, because if you were doing that, you'd say, well, we're not designing a library anymore, we're designing a hospital. I don't, clients, there's a really funny Monty Python skit. Anybody Monty Python fan? There's a really funny Monty Python skit where these clients are, they're bringing in architects to design apartments. And so this guy comes in and starts talking about the slaughterhouse that he's designed for him. He's like, we didn't want a slaughterhouse, we just wanted a block of flats. It's like, are you sure? This would be a really great inclusion. So I encourage you to look it up. But that's what so when I said decrease the load, like you said decrease the load, what does that mean? Well, first off, let me say this. If the beam is too strong, we actually probably wouldn't want to decrease the load, we want to increase the load. So that's actually probably backwards. Probably need to say increase the load. But what does that mean? That means increasing the tributary area. That's what that means. Yes.
So if you change your D very much at all, are we worried about the B to D ratio?
At that point, no. I mean, because that's a good question. Keep in mind, it's an approximate B over D ratio. And the B over D ratio is just a tool that we're using to come up with a trial section. In the end, what really matters is phi mn being greater than or equal to mu and having a beam that's efficient. That's what matters. So honestly, I couldn't really care less what the B over D or the D over B ratio is as long as the beam works. That's a good question, so this is good stuff. Any other questions? I like this. All right. I'm giving you these options because during iteration on homeworks, I think you need some guidance. This would be some good guidance. All right. Now, I really briefly want to mention this. This is designed for a known cross-section. So this is a little different. This is if you're using something like a precast element or using ready-made forms where you know what the beam looks like, and the only thing that you need to determine is the area of steel. This is actually a really easy design problem because there's not as many variables. The size of the beam is locked. So the only thing that you need is AS. And in order to get that, we're going to use rho values. But the rho value that we're going to use is a little different. Okay? What I mean by that is this. So when we're designing a known cross-section, remember this equation that we derived, right? If the cross-section's known, then the only variable is rho. That's the only variable. So if I factor that a bit, just rearrange it a bit, doesn't this kind of look like a quadratic? Like a pile of junk times rho squared minus rho plus a pile of junk, like my efficient use of terminology, pile of junk times rho squared, like that. So if I have a quadratic equation, I can take that quadratic equation, throw it in this thing called the quadratic formula, and solve for rho, right? Make sense? And so once I solve for rho BD will give me the required area of steel. So when we design for a known cross-section, the only assumption that we have to make is phi, because we don't know what phi value is because we don't know what the strain in the steel is. We don't know what the strain in the steel is because we don't know what the steel looks like. But we compute the factored moments on the beam. We don't have to assume a beam self-weight because we know what the beam looks like. So there's no assumptions there. We compute mu over phi to get Mn required, and instead of using this rho value that we're just picking out of the sky, we're actually solving for rho for our beam. So it's a lot more scientific. So we solve for rho BD, pick a pattern. So known cross-section problems are a lot easier. Okay, they're a lot easier. They're a lot shorter. Okay, so next time we're going to have this. We're going to do this problem, and so what we're going to do is this. We have a beam, and we know what the beam looks like. We know it's 16 inches wide and it's 21 inches tall. And to make your life easier and to make this problem shorter, I'm going to go ahead and tell you what mu is. Instead of having to go through WL squared over 8 and factored loads and all that, you already know how to do that. So I'm not going to make you do it twice. So next time we're just going to say, here's my mu value. So step 1 is going to be write down mu and move on. What's the area of steel required? And so it's going to be a really short example. So we'll start that next time, and then we'll get into slab design. Okay? Slab design and known cross-section design are pretty much the same thing. The only difference is in slabs, what you're doing is you're picking a pattern of reinforcement and you're just repeating it over and over again. But it's a really simple, straightforward process. All right. That's all I got. I will see you all, or at least most of you, in about 10 minutes.